Okay, so see, my dear student, my request is please be interactive. Otherwise, learning process is really incomplete. If you don't interact with your instructor or your teacher, learning process is completely failure and completely incomplete. Okay, perfectly incomplete. So please feel free to ask any question, and if you don't understand any term, any concept, you can ask me either through chat box chatting, or maybe you can unmute yourself and speak to mic. Okay, this is my request. Otherwise, I don't know whether you people are understanding or not. See, there may be very intricate uh, details, and few of them, if you just leave a few intricate concepts, then it is very difficult to crack competitive exam. Maybe you can pass nicely with nice grade. A board exam you may be able to pass, but uh, cracking competitive exam is not so easy unless you understand each and every concept. So please feel free to ask. Okay, yeah. So before I start today's class, I have an important like discussion with you people who are coming regularly. We are thinking, see, our platform is for NEET and JEE, okay, those kind of, or any other competitive exam platform. Okay, so we must focus on solving questions of that standard, like NEET and JEE standards, or we should discuss concept of that standards. Okay, but see, 1 hour or weekly 2 hours are not at all sufficient. Okay, so sometimes people are like, you are coming here, people are coming like 10 minutes late, and then like as soon as 7 o'clock, if people are leaving the class, leaving the meeting, that is okay. Maybe you people have something, some other classes also. I agree with you, but you will have to actually. We are planning to extend our help little more towards you. We want actually you will have to cooperate with us. Let's see. We want to increase 2 sessions more. 2 sessions more. It can be either a single class or 2 classes again. So I am thinking that the Sunday class I'll be making as 2 hours class, and that class will be mainly focusing the NEET and JEE question papers and related concept and numerical problem solution types. Okay. And one more thing I am going to implement is that the assignment part. Okay, assignment part, or sometime maybe quizzes. You can say that is a quiz. I'll make a set of questions. First, you will be given for the beginning. We will be giving you the sheet, question sheet. You have to solve and properly written your name and all. You have to send the PDF to Guna madam, so that she will be delivering to me, and then I can check and I can see how much progress you are like making every week, or where are the weakness for individual students. Okay, so that I can discuss. And another thing is that you people have to interact while taking a class of this numerical solve and like solution, when I'm going to discuss like this kind of concepts and solving some numerical questions, etc. You people have to interact with me. Sir, this place I couldn't understand. That place I don't understand. So how do you do that? Kind of those things you can ask me exactly when the class is going on. Okay, I'm ready to help you. I'm ready to help you to understand concepts. Okay, otherwise it will be just like a class, and it may not help you to crack any competitive exam. Okay, this is my uh, brief note for you to do. Then what you have to do, either you can message to Guna madam or talk to her, or maybe you can tell me now itself. I will write down which day, like each of you which day. Like anyway, Sunday class I'm going to make it 2 hours class. If you tell me that make it 6 to 7, then I'll make it not 6 to 8, or maybe 5 to 7. So whatever you like. Then another option was like Saturday. I don't know how many of you have school or how many of you are free on Saturday. So Saturday at least if we take 1 hour, so then Wednesday, Sunday 2 hours, Saturday another 1 hour. So total 4 hours session we'll be having in a week. Okay, so this is just to help you because physics or maybe any subject when you learn for competitive exam, you need to spend time. Okay, you have to spend a lot of time. Then only you can crack any competitive exam. Okay, so if people can discuss among yourselves, or you can just give your individual convenience to Guna madam, and then she will just see how many of you are having the same time frame or something like that. According to that, we'll take a decision and then we'll implement. Most probably this Sunday I'm going to make this class as 2 hours class. So you can tell me whether I can start at 5 to I can start at 5 and finish at 7, or 6 to 8, which will be convenient for you to do. Okay, so accordingly I'll be doing. So one more question I have in my mind, since this platform you are coming for competitive exam, so is it necessary that the text itself I'll be teaching you thoroughly, or I'll be going concept by concept and solving more problem rather than telling about like very simple concepts in your NCERT text? Can you people message right now? Should I like help you in board exam, for board exam also, or only for the competitive exam? So in that case, quizzes I'll be setting up question in that standard. If you feel like I have to help you in board exam also, then maybe 30% board exam and maybe 70% competitive exam. Kind of those, like I'll make kind of that. Okay. So students, please write in the chat box. If somebody can speak, they can speak also directly. Yeah, you can see there is a chat option, okay, for every one of you. We are trying to help you, so you have to cooperate, you have to speak with us, you have to express yourself so that we can help you like again better. Okay, so I'll just wait for two more minutes to get your response, otherwise I'll start the class. Actually, I asked you whether you need help for board exam also. Another question, whether you will be able to attend 4 hours session per week. We are having Sunday and Wednesday classes. Now, which day you will be comfortable to have another 2 hours class? That's what I asked. Okay, anyway, do one thing, if you can respond to Buddha Madam as well. So maybe later after the class, let us not waste our time now. Already 15 minutes over. So yeah, we'll just start our session today. See, the last day we started with this magnetization and magnetic intensity part, this part, and I could not complete the concept that day. So I'll just recap somewhat and then complete this. Then I'll go to the next part of the chapter. Okay. Look, in this actually, like all around our world. So we have many types of materials. Okay, elements, and we are making many synthesizing many alloys also. But how to classify them? Like what magnetic properties each of them has. Okay. So how to classify them and which category, like how many classifications are there in magnetic materials? Okay. So whatever you see in our nature, magnetic materials can be divided into or classified into three fundamental, three main categories. Okay, three main categories. Those are diamagnet, diamagnet or diamagnetic material, then paramagnetic material, materials, and third is ferromagnetic material. So these are three main categories of magnetic material. Okay, but how to distinguish each and every material, or yeah, how can we distinguish diamagnet over paramagnet or paramagnet over ferromagnet or vice versa? So for that, we will learn today few parameters. Few parameters. So those are like magnetic induction. Then we'll be learning magnetization. Okay. Then we have magnetic susceptibility. Susceptibility. We have magnetic permeability. Okay, these are the terms, and obviously few more terms will be learning over there. Relative permeability kind of those. Okay, so we'll be learning these parameters to classify materials into these three categories. So let us first start with magnetization. What is magnetization? So what is magnetization? Magnetization actually it is defined as the net magnetic movement. It is a vector quantity per unit volume of the substance. Okay, it is denoted by capital M. This is magnetism. I'll tell you what is. We have learned in the previous chapter that the origin of magnetization is a dipole, magnetic dipole or circulating current, right? Circulating current. So circulating current is the origin of primary origin of or basic origin of magnetism, okay, or magnetism. Circulating current. This circulating current are equivalent to magnetic dipole. Magnetic dipole. So you have already learned electric dipole. So electric dipole, you have positive and negative, then it is like that, and they have a parameter dipole moment. Okay, magnetic dipole, electric dipole moment. Similarly, when you have magnetic dipole, you have magnetic dipole moment also. So what you have magnetic dipole, magnetic dipole moment. Now, see if I take a bulk material, any bulk material like this. So they have lots of atoms inside, right? They have bonding between each other. Suppose this is a solid system. So magnetism can be seen in gases as well. Gases and liquids. Some liquids also you can see magnetism. It's not like that. Like solid atoms only can see so magnetism. It's not like that. Even gases also like oxygen gas in STP, nitrogen gas in STP, they exhibit magnetism. Okay? So when you have all around atoms close back, see what I told in an atom, electrons are there. So those electrons will be circulating, right? They are orbiting around the nucleus. So they are orbiting, that means the motion is happening. And look, so it will constitute a current. This is called electronic current. Or on water current, I can say this is the amount of charge E suppose in one time period. So this is the current. Okay, and you know that T is equal to 2 pi R by V. This we have already learned 2 pi R by V. So if you just see that from here you can derive something called magnetic moment, which is denoted by MUL, that is orbital magnetic moment. L means orbit. Okay, so orbital magnetic moment. So you can see in a bulk system or bulk material, there are atoms, and atoms are circulating around the nucleus. So they are constituting a current. And whenever there is a circulating current, so electron, this each orbit, like each atom can be thought of actually having a circulating current. Okay, circulating current. Okay, so whenever there is a circulating current, I can say that will act as a magnetic dipole. So magnetic dipole in general, you will see in the math lesson, they are denoted by a line with the arrowhead, with an arrowhead. Okay, arrowhead like this. Okay, so these are, so in any substance there are not all substances obviously, some substances they have already some magnetic dipole moment. So suppose I have magnetic dipole moment for each atom, then I can know by particular volume how much net dipole moment is there. Okay, so if all the dipole moments you are adding them up, because the bulk material is having lots of dipoles, because there are many atoms, and each atom electrons are circulating, at least the atom's electron is circulating, and that is constituting a current as well as the magnetic dipole moment. So all of this magnetic dipole moment in the substance, when they add up to keep certain net magnetic dipole moment, they will add up. All of them will add up for each individual atom. They will add up to a bigger value or net magnetic dipole moment. This is called net magnetic dipole moment. Dipole moment. So magnetization is defined as the net dipole moment per unit volume of the substance. Per unit volume. So magnetization is defined as the net magnetic dipole moment part unit volume of the substance. See, M magnetic by M net by V. This is actually defined as magnetizing. Okay. So if any material has net dipole moment, then only there will be magnetization inside the material. I hope you understand that. Okay, all right. Now see, we have learned. See, I'll tell you what is induction and what is magnetic field intensity now. Magnetic induction versus magnetic field intensity. Intensity. Okay, I'll talk about here these things. See, when I'll just take it, like to get an NC, there are many magnetic materials in the nature, like iron, cobalt, then many other like nickel, etc. But do they attract each other? Two iron fields, whether they will attract each other? Answer is no. Two iron fields will not attract each other, neither they repel. That means they don't have magnetization as it is. So what we have to do? We have to apply external magnetic field. Okay. So apply external field to magnetic field, mag field to magnetic material to magnetize them. Magnetize. Okay. That means if you have an iron piece or any other magnetic material, okay, so you just put it in uniform magnetic field, inside uniform magnetic field, then what will happen? It will be magnetized. So material will be magnetized. Obviously, there are some physics inside this also. We'll discuss in the next section. So let me just tell you what is magnetic induction and what is magnetic field intensity or magnetic field simply. See, to magnetize a material, you have to apply external field. So very simplest way is to magnetize a material is just use a solenoid. Okay, the solenoid you just coil your wire around it and then connect a battery DC or AC whatever you like, and then pass the current through this. So the magnetic field will be created. Suppose this is the side, not pole. So magnetic field will be like this, again like this. So magnetic field will be created. Okay, inside the solenoid. Okay, and magnetic field is always axial in solenoid. And what is the magnitude? Magnitude is mu 0 in R. That means what is the N? N is the number of turn. This number of turn. Then R is the total current which is flowing through the circuit. This coil for the battery. And mu naught is called permeability. What is this called? Permeability. Permeability in free space. Free space. What does this permeability mean? Permeability means it will permit magnetic field lines to pass through a certain region of space. Okay. Suppose it is free space. See, if I take an airport solenoid means nothing is there in between the no. This is only air is there. Okay, airport solenoid. This is called airport solenoid. Okay. So if you have airport solenoid, so magnetic field will be created in the air itself. Okay, and that magnetic field, suppose this is like this. Okay, so magnetic lines will be created inside the core, air core, solenoid, and this is denoted by D0 because it is in the air. So suppose this is D0. So this magnetic field, okay. Now this is actually the magnetic field created by the current going to the okay, going to the wire. Now instead of this air core, if you put a magnetic material, okay, you're just putting a magnetic material which has certain magnetization in that material. Okay, you just put a magnetic material which has certain magnetization inside it. Okay, if you put it here inside the solenoid, this is called suppose this is called soft iron or something. So this is called soft iron core material. Iron core uh, solenoid. Okay, soft iron core solenoid. So what happens in this case? Solenoid. So what happens in this case? What will be the magnetic field now inside the solenoid if okay if this solenoid is actually completely filled with this material, then what will be the magnetic field now here? Will this be B0? Certainly not. Certainly not. It will be something else. So that is, if I write B, this will be B0 plus. See, I have a material. I have now taken a material here inside which has some net magnetization M. Okay. So there will be another term which I am writing here as BM. So this magnetic field, this is called actually magnetic induction. As it was, this is called magnetic induction. See, earlier it was called magnetic field, but it is now magnetic induction. Magnetic induction. Why? Because it is now happening inside the material. Magnetic induction. Okay, it is happening inside the material. Something is happening inside the material. See, I would have seen if you keep one neutral electrical and neutral object near a like negative or positive charge object, so there will be some uh, electric charge induced in this material. Similarly, if you keep a material inside a magnetic field, so where B0 is the external magnetic field which we are applying to current here. See, we are applying current. So magnetic field air from solenoid was creating B0, and that B0 is actually now applied to this material, in which now the magnetic field will be this one. So you can see this magnetic field is not in the air now. This is the magnetic field inside this material. So that's why this much magnetization has been induced to this material. So this is called magnetic induction. Sometimes this is called flux density also. Flux density. B is called flux density also. Okay? That means, like from the Gauss's law, we know phi flux to any closed loop will be B into A. So this is actually flux. This is B into A. This is the area. This is the magnetic field at any place, and it's fully closed surface. And see, B will be pi by A. Pi by A. So this is a flux pi and divided by area. So this is called flux density. So this is called flux density. B is going to be pi by A. This is called flux density. That's why sometimes you will see the unit of B will be omega per meter square. Per meter square. Sometimes. Okay? Because it is called magnetic induction also. It is called magnetic induction also. That's why it is. Sorry, it is called flux density also. Okay, so when it is called flux density, the unit will be omega per meter square because this flux has unit omega. Okay, flux has unit omega. This is the reason. So I hope you guys have understood what is magnetic induction and what is magnetic field or external field. Here I will explain this. So I have got magnetic induction inside the material. If I write in terms of vector, let me write this, and this is a Bm. You know, this is Bm. I am writing. So because this, let's talk about Bm also here. See, this Bm is actually the induction happens inside the material. Okay, inside the material because it has certain magnetization end. Certain magnetization end this material has now. So if that is the case, then this induction will be directly proportional to this magnetization. This Bm. Induction will be directly proportional to the magnetization. And if we just remove the proportionality, then you will look here. We have mu 0 m. So magnetic induction, which is happening due to the magnetization in the material itself. So that is mu 0 m. So I can write as a whole B is equal to. So this is also magnetization is also a vector because dipole moment coordinates on it. Dipole moment is a vector, so magnetization also is a vector. So B is equal to B0 plus Bm. I am writing here now mu 0 m. So this is the equation we have got now. So this is actually the field of solenoid. This is the material. So after going down the solenoid have this much magnetic. Like this is called actually the magnetic induction. Okay. Alright. So this left hand quantity and this B0, you might be thinking this is in the air, and this is inside the material. Inside the material. Okay. So yeah, when it is inside the material, it is called magnetic induction. And when it is inside the like it is outside or in the air, then it is called magnetic field. Magnetic field. That's all. And magnetic magnetic flux density. You can say this is called magnetic field. Okay. Or sometimes this can be called as external field also. External field because it is produced by the current in the solenoid coil. External field. I hope you guys understand this. Now, see, I defined another term which is called H. So this is called magnetic field intensity. Magnetic field intensity. This is another form of actually external magnetic field. Okay, see, it can be written as into H. Okay, this is the relation between magnetic field intensity and magnetic field in air. So what is intensity means? See what I am saying. Why this B0 is what is the action of this B0 or H0? The action of this B0 or H0 is to magnetize the material. Okay, magnetize the material. So field intensity means the strength. It is the strength. Okay, the strength. Strength, or it is the measure of strength. Measure of strength of applied field to magnetize a material. The magnetic field intensity means how strong it is and how much magnetization can be induced to a material. So this is denoted by actually H. So this is called magnetic field intensity. Magnetize a material. It is a measure of the strength of applied field. Okay, applied field. Obviously, here I am talking about magnetic field. Magnetic field to magnetize a material. Okay, I hope you understand this. If not, you can ask me. What is magnetic induction? What is magnetic field intensity? So this is the external region actually, external part, and induction is actually happening inside the material. So that is what you have to understand this thing. Even B0 was outside the this is in the air. Okay, but this B, what is producing now, that is inside the material. That's why this is called induction. These are called magnetic field mass density, and this is called magnetic field intensity. Okay, so what is the relation now? So I have got B is equal to induction is equal to B0 plus B0 M. So look, this B0 I can write even this as this. Okay, okay, I'm writing vector. So both sides I have to write vector. Sorry, this is not a vector. This is the vector. Okay, all right. Now one more thing. See, I'm telling that this magnetic intensity is the measure of how much magnetization can be produced in a material. That means this H will be influencing this magnetization also. Okay, and how this magnetization will be influenced? It will be influenced directly proportional. Okay, if the magnetic field intensity is increased, magnetization also will be increased. How it is? See, if I think that they have dipole moment inside the material, okay, inside the material, dipoles are actually randomly oriented due to thermal energy or thermal vibration. Okay, when you apply this magnetic field intensity from outside, these dipoles will be trying to minimize their potential energy. If you remember, potential energy is minimum when the dipoles are parallel to the field, external field. So they will try to orient towards magnetic field. So then what will happen? You will get like net more and more net dipole moment you will get. When they align towards the field, you get more and more net magnetic dipole moment. Then you divide the volume of the substance, you will get more capital M or magnetization. This is how magnetization is actually directly influenced by applied field or external field. I can write this. So if I remove the proportionality, then look what I can write. I have to bring one constant of proportionality, which I am writing here as chi. This is called chi. Okay, into h. Okay, chi into h. So what is this chi called? This is called susceptibility, magnetic susceptibility. Okay, this is called magnetic susceptibility. Susceptibility. So this is called magnetic susceptibility. And you know, this magnetic susceptibility is a material property. Okay, this is a material property. This varies material to material. That's all, depending on the value or nature of this or sign of this susceptibility, we can classify materials. Okay, it can be either positive, it can be negative also. It can be positive or negative. Okay, susceptibility can be positive, negative. It can be larger, it can be smaller, it can be very larger also. Okay, so I'll clean it here. What I have got now, see, I had this, then I had written mu0. Okay, I'll write the master equation once again. B plus Bm, B naught plus Bm. Okay, so this I have written as this, and this we know mu0 M. Okay, and look, this M also can be written as mu 0 and then current into H. Okay, if in place of M I am writing this. Okay, this I am writing. Okay, so if I take mu 0 common and H common, what I take 1 plus chi. Okay, and see this mu naught 1 plus chi into H. So this term 1 plus chi, this term is written as mu r. Okay, mu r and H. And as a whole, mu naught into mu r will be written as mu. That is the magnetic permeability of the substance. So what I have got here, what I have got, B is equal to mu into H. Okay, this is inside the material. This is not mu zero. Here, this is not mu zero. B is equal to what I get. This H will be the vectors. On the other will be vectors. So what I get is mu into H. This is not mu naught. This is actually this mu is actually mu not into mu one. So what is mu naught? Mu naught we have written as a 1 plus phi. 1 plus susceptibility is called relative permeability. So this is called relative permeability. Magnetic permeability obviously permeability. Okay, so this is called relative permeability. Look one thing. See, I was writing that M is equal to phi into H. So here, this M and H, they have same unit, ampere per meter. Okay, that means this chi is a dimensionless quantity. Dimensionless quantity. Okay, dimensionless quantity. Again, what is chi? Chi means mu or I can write mu of is 1 plus chi. So this is for relative permeability, and so this is for relative permeability. This is called magnetic susceptibility. This is for magnetic susceptibility. So they have a relationship mu r is equal to 1 plus chi. So since this, again, one more thing, since this is dimensionless quantity, so this is a number again. So mu r is also dimensionless quantity. Mu r is also dimensionless quantity. This is also dimensionless quantity. Okay. Alright. So I hope you guys are understanding. This is called relative permeability. And see, it is actually obtained as mu by mu naught. So magnetic susceptibility of the substance divided by permeability, magnetic permeability in the vacuum. That means, if I keep a material, magnetic material, if I keep a magnetic material, it has some susceptibility, some permeability. Okay, and the vacuum also has certain permeability. But see, if I keep this material inside a field, inside a field, inside a magnetic field, applied magnetic field, which is, see, applied magnetic field is outside. So how many magnetic field lines will penetrate or will be able to pass through the material or concentrate in the material is called relative permeability. Okay, over free space, how many magnetic field lines are penetrating or getting into the material is actually defined, or that measure is that actually relative permeability will give you the measure of that only. Okay, measure of that. So this is all about this terms. Okay, so what we have learned so far, I just summarize what we have learned. We have learned what is called magnetic field flux density, or what we have learned magnetic field intensity. Then we have learned what is called magnetic induction. Then we have learned what is magnetization, and we know what is the relation between magnetization and H. So magnetization is actually chi into H. Okay. So from here I can write chi is equal to M by H. Okay. I can write this as well. And then we have learned that this is a dimensionless quantity. M and H, they have both unit as ampere per meter. And relative permeability is defined as 1 plus chi. So 1 plus chi. And this is the main important parameter. This chi and mu r. These are the main parameters which will help us to classify, different materials or materials into different categories. Materials into different class of class of magnetism. Okay, different classes of magnetism. Okay, well, I'll show you in your, see, as I said, the sky can be, it can be positive, it can be negative as well. Okay, so positive plus para or ferro, okay, para or ferro, and negative is diamagnetic material. Okay, we'll see here. In your book, I'll show you a table, very nicely given over there. So all of you should learn here. So see here the B, this is the induction. This is happening due to, see, external region, this H, and this internal region, that is the magnetization. So it is actually defined properly. You can see that. And see these are materials: bismuth, copper, diamond, gold, lead, mercury, nitrogen, silver, silicon. These are all actually diamagnetic material because they have susceptibility negative. And the materials which have positive susceptibility are called paramagnetic material. Look here: aluminum, and calcium, chromium, lithium, manganese, magnesium, even manganese, chromium also. They are paramagnetic. Okay? Because the susceptibility, negative means I'll tell you, if the susceptibility is negative, what happens to the mu? See, I have a relation. I have got a relation. I have got a relation between chi and phi. Is other way, mu r as 1 plus chi. So when chi is negative or minus 1, suppose minus 1. So what will happen? Mu r will be 0. That means what I told mu r means how much magnetic field lines are allowed inside, okay, or permitted inside. So if this is 0, in such case when the susceptibility is, suppose if it is like larger than minus 1 or anything, if this chi is negative quantity, any negative quantity, so relative permeability will be very, very low when it can go to 0. In the case when I is minus 1. So if relative permeability is 0, permeability is 0, then no magnetic field line can penetrate. Rather, magnetic field line will be repelled. Magnetic field line, if you keep a diamagnetic material which is susceptibility, I suppose perfect diamagnet has a susceptibility minus 1. So when you just keep inside a magnetic material, what it do, it will repel the magnetic field line. So magnetic field lines will be bending like this and more. Okay? So magnetic field lines will come and all the way to bend and go. In this way also, see, this will pass here, this will pass. But see, the magnetic field lines here, they will be repelled. So they will not penetrate through the material. Okay? They will not penetrate through the material. Okay, this is called reflection. Okay, sorry, this is called actually it's called expel. Okay, it is the magnetic material is expelling, expelling the magnetic field lines or repelling the magnetic field lines. Okay, so this is actually yes, this is the case of perfect diamagnet. I just discussed it, but see, depending on these values, different values of these parameters, like see, permeability or susceptibility, we can define various materials like we can classify materials into three categories: diamagnet, paramagnet, and ferromagnet. Look, the paramagnet has actually I much greater than 1. Relative permeability much greater than 1. It can go even some cases 100 to thousands also. Like very soft ferromagnetic material, relative permeability will be very large. Okay, and so the magnetic permeability in that material will be very large, very much larger than the relative permeability in the metal. Okay, so in case of diamagnet, you have susceptibility negative to 0. So you have mu r, that is the relative permeability in between 0 to 1. Okay, relative permeability when I have told you that when susceptibility is -1 for a basket diamagnet, then mu r will be actually exactly 0. Okay, and in this case, the magnetic see the mu magnetic permeability is actually less than mu 0. That means the magnetic field lines will be expelled to the platform rather than concentrating inside the material. You can see this. This is the diamagnetic material for which actually this is not constant exactly -1, but it has less permeability. That's why only one magnetic field line has penetrated that material, and other field lines have been expelled out. Okay, or repelled out. So this kind of that's why. So this kind of magnetic. This is the paramagnetic. For this kind of material, when you keep a diamagnetic material, okay, inside a see, if you just suspend, if you suspend a diamagnetic material, if you suspend a diamagnetic material, suppose this is your north pole, this is south pole. If you just suspend with a string a magnetic material and switch on this magnetic field, you know what will happen. So, as I suppose in the beginning it was like this way. So, as soon as you apply the field, so field lines will be like going like this. So, field is here, and in this region actually field will be maximum, magnetic field will be maximum. So, this diamagnet, what it will do, it will actually orient themselves, okay, perpendicular to the field, perpendicular to the field. So see, this will be orient like this, perpendicular to the field. Why? Because this diamagnet, since chi is negative, so diamagnet will repel the magnetic field lines. Okay, magnetic field lines. So this is why they will be, as soon as you keep inside the magnetic material, sorry, inside the magnetic field, if you just suspend like this, in the beginning, suppose it was like that, it will be immediately perpendicularly situated with the magnetic field. Why? Because it is repelling the magnetic field. Okay, that's why. Okay, so yeah, so this is the case. And because of the same reason, if you have suppose non-uniform magnetic field, suppose you have like this non-uniform magnetic field, so what the density of the field lines is more, there will be magnetic field will be more actually. There magnetic field will be more, okay, and there magnetic field will be less in this region, sir. Because density is less. So if you keep a diamagnetic material, you know what to do. So this diamagnetic material will move from high field region to low field region. They will move from high field region to move from high field region to low field region. Okay, so because the same thing susceptibility actually they don't allow magnetic field lines or repel the magnetic field lines. That's the reason. Okay. Okay. So with this, actually, see, I'll just few more like what I'll tell about diamagnetism, then I'll stop the class. Okay. Because most of the people have already left. Only you people are there. So I'll just tell you few what just stay for 2-3 minutes. See, diamagnet has few properties. I'll tell you. Then next I'll teach you the paramagnet and paramagnet, etc. So you look what diamagnetism occurs. Diamagnetism occurs due to orbital motion of electrons. You know what happens? Okay, so I'll tell you what happens there. See, as I said, that atoms are there, electrons are moving around. Okay, so like revolving around there, and then they also constitute a current. Suppose electrons are moving in this way, so current will be actually produced in this way. If this is the direction of current, then you know how to calculate the magnetic dipole moment. Okay? Suppose I am taking that the applied field for applied external field is in this direction. Okay, in this direction, suppose, and then if you have electron revolving in this direction, current will be produced in this direction. Okay, the current is produced in this direction. No, that is in the clock, like yeah, clockwise direction. So if it is the clockwise direction, so your magnetic moment will be actually in this direction. Okay, downward direction. And in some cases, if the electrons are revolving clockwise direction, so current will be anti-clockwise direction. Okay, so your magnetic moment will be upward direction. So in the direction of the field. Okay, in the direction of the field itself. So what happens due to the property of this susceptibility is -1 or something like that. Okay, so less than 0. So in this case, what happens? See, there are maybe pair of electrons. Those electrons which are moving clockwise direction, they will create a magnetic moment along the direction of field. But this will not happen. So the electrons will be slowed down. Actually, these electrons will be slowed down. Start creating magnetic dipole moment along the same direction of the external field. Will be slowed down so that the dipole moment along the field will not be there after some time. So it will be decreasing. Dipole moment, the value of the dipole moment will decrease. Sometimes it will be 0. But the circulation of the electron or the direction of the circulation of the electron happens in that direction, like in which the magnetic dipole moment is anti-clockwise to the field. Okay, this is mu L and this is B. So when this happens, so that motion, in this case, suppose anti-clockwise, so this will be actually speeds up. This electron will speeds up. Okay, speeds up. So that's how they will create. See, this is the external field. So this will be your magnetic moment. So external field, magnetic moment or magnetic adjacent, you can say. So magnetization will be always opposite. Okay, anti-parallel. Anti-parallel. We will be always anti-parallel to this magnetization or magnetic moment. So because of that, the susceptibility. If suppose I had told you that M is actually IH. So if suppose my direction of magnetization is opposite to this, so there will be minus sign over here. Okay. So I will be what? So I will be minus M by H. If these two are in opposite direction, okay, then only you will get negative susceptibility. This is the origin of negative susceptibility or diamagnetism. Many examples which I have shown you, that Bismarck, then silicon, then acid nitrogen, gas, etc. These are actually examples of diamagnets. Okay, so you guys should read up to this portion, and then I'll discuss the rest of the part. I think I'll take another class to finish this chapter itself. Okay, so yeah, so this is all for today. I'll stop it here. See you guys on Sunday again. Obviously, there will be some changes on that classes, like on that class. So please like respond to Puna madam about your view or your opinion about the like extension of the class hours and etc. Okay. Thank you very much for your patience. So bye for today.